So today we are going to start lecture 12 on our helicopter dynamics course, and today I am going to discuss why the modes which we discussed in our previous class are normal. So these modes are essentially perpendicular, and we are going to prove that in today's class and see why that's a very important concept in dynamics. I am Dr. Ranjan Ganguly. Now let us extrapolate our 2 degree of freedom system to a multi-degree of freedom system, such as this given here, where there are a series of masses connected by a spring. And this could be a general spring mass system of any sort. And in the end, we know now that if we were to derive the equations of motion for this system, we are going to get a matrix differential equation of this form: m w double dot plus k w equal to 0. So that's a differential equation that has a size given by small n. So essentially m and k are the mass and stiffness matrices of the system, and w contains the degrees of freedom of the system. Now once we have got the governing differential equation for this multi-degree of freedom system, we can get its frequencies and its mode shapes. Now this system has n modes. So we can say that any mode number r is given by phi superscript r. So this notation means that it is the mode number r for the corresponding system. Now from the definition of the mode, we know that this mode is a solution of the differential equation, and therefore any mode must satisfy the differential equation. So if we were to presume typical harmonic motion and express w in this form, w is phi r into e to the power of I natural frequency corresponding to mode r into t, and then substitute this back into the differential equation, it should be satisfied. So that's what we are going to do. We are going to substitute this presumed solution into this differential equation. So let's do that. Let us substitute this solution here. So that is for mode number r. Now we can have one more mode, say mode number s, and we can also substitute that particular solution into the differential equation. And so we are going to get two equations, 1 and 2 here. So number 1 corresponds to mode number r, and number 2 corresponds to mode number s. So let's see how you would get this equation. If you were to substitute this here, you would of course get a term k into phi r, and then you would have a second derivative of this term here. So essentially that's a time derivative, so only this part gets differentiated, and so you would get a frequency squared term here. You would get a -1 because I square is -1, and then you would get the m here. So sometime I'm mixing capital and small m, so don't mind that. Now once I get these two equations, I'm going to proceed forward with these two equations and do a lot of pre-multiplication and post-multiplication and prove that these two modes are normal, that is phi r and phi s are normal in a certain sense. So let us take those two equations we got from the last slide, number 1 and 2, and pre-multiply them by phi st and phi rt. So essentially the equation which contained phi r is pre-multiplied by phi st here. So you see the entire equation, all the terms are multiplied by phi st. Similarly, in the second equation, which essentially contained phi s, we pre-multiply by phi rt. Now what we do is that we take the transpose of equation number 3. So if we take the transpose of equation number 3, what would happen is that you have a typical formula for matrix transpose. AB complete matrix transpose is BTAT. So essentially if we apply that here, if this is A and this is B, so then B gets transposed. So we would get one value here and one value here. So if we were to do that, we can clearly see that, let's say this is A and this is B. So we would get phi RT, then MT phi S here. So what this would do is it essentially creates one more equation. And now I use the fact that the mass and stiffness matrices are symmetric. And what that means is that the transpose is same as the starting matrix. So MT equals M, KT equals K. And if we were to apply that, then essentially this would become M, this would become T. And why we did this whole exercise is that we wanted to get rid of one of these terms here. So now if you look at equation 4 and equation 5, you're going to see that these two terms have become similar or exactly same, because remember K transpose equals K. So if I was to subtract these terms, I would essentially get an equation in terms of this phi RT and phi S into this and this. So this frequency square and this frequency square would get subtracted, this term would be removed. So that's what we are going to do in the next slide. So we subtract 4 from 5 and we obtain this equation here. Now you can verify that by doing it yourself, and this is very important equation because this is telling you that for all cases where R is not equal to S, that means these two are different modes. So in those cases, the frequency not being same, this particular equality or equation holds, that is phi R transpose M phi S equals 0. This is a very important piece of information, and it's so important that I have put this in a complete slide here. And it's basically telling you that whenever you have two modes which are not the same, that means they are different modes. For example, it could be mode 1 and mode 2 or mode 3 and mode 7, like that. Then phi RT M phi S equal to 0. And this is essentially saying that these modes are normal with respect to mass. Now we can prove one more fact relative to stiffness. So let us again go back to equation 4 and 5 which we had derived before. And in equation 4, I'm going to pre-multiply this equation by phi s square. So I do that here, I get this here, remembering again that mt is m and kt is k. And I'm going to take the equation number 4 and I'm going to pre-multiply that or multiply that by omega r square. So that is done here and that yields this equation. Now why did I do all this? Well, the reason is that I want these two stiffness terms to now become same. Okay, in that sense that these two are there and I can then subtract these two terms here. So essentially now if you look at these two equations carefully, you will see that this term here is same as this term here. And this setup means that if I subtract these two equations, I'm going to get rid of this mass term. And so if I were to do that, I would essentially get a term involving only the stiffness part of the equations, and I would get this frequency of S mod square minus frequency of Rth mod square. So subtraction would yield us this, which you can see clearly here when I have written out these two equations, and the multiplication of the frequency square has ensured that this mass term has been put to 0 when we subtract. So now this equation is also another very important equation, and you can straight away say that when R is not equal to S, one more normality holds here, and that is that phi RT K phi S equal to 0. Very important concepts. Now finally we are going to state a very important result in terms of the mass and stiffness matrix. So we define something known as the Kronecker delta. And the Kronecker delta is 1 when R is equal to S and is 0 when R is not equal to S. So this delta is the Kronecker delta. So, so always remember that this is 0 whenever R is not equal to S. That is a very easy way to remember that. And so it's 1 at only one particular point. Now this Kronecker delta lets us write out the basic fact of what the normal modes do to the mass and stiffness matrices. So here you can see that when we do this phi r transpose m phi s, we are left with delta rs into mr. And what this is telling you is that all the non-diagonal terms of the modal mass and modal stiffness matrix will become 0. So essentially when this action takes place on the typical mass matrix, it diagonalizes the matrix. When this action takes place on a typical stiffness matrix, it again diagonalizes the matrix. So these are two very important things which we can clearly see here. And there are a lot of practical implications of this, which we will see in later lectures. Essentially, when we typically derive mass and stiffness matrices for any multi-degree of freedom system, they are fully populated or substantially populated matrices, I should say. And so when you apply the normal mode transformation to them, this particular thing we are doing here, the phi r transpose into the matrix into phi s is known as the normal mode transformation. It essentially diagonalizes those matrices. So it will convert the multi-degree of freedom system into a number of single degree of freedom systems. And that is a very important fact which is often used by the normal mode transformation, that it tends to diagonalize the matrices, and diagonal matrices are simpler to work with. And also one more fact which we will see in the next lecture is that you don't need to retain all the modes. The first few modes are sufficient to capture the dynamics of a system. That is one of the key benefits of the normal mode transformation. And effectively, once you have converted the given equations to the modal space, you need to retain only the first few modes to capture the structural dynamics of the system. So I will stop my lecture here. I will see you in my next video. See you then.